Okay, I think we could get started. So welcome to Elm, where I learned to love front-end development. We are not so many people. Probably Elm is not so trending here a lot. Let's hope it will grow in the next years. So just go with the boring stuff. Who am I? I'm Marco Perone. You can find me on Twitter as Marco Shuttle or just at my email. I am currently working at the company Envy Labs, which is just a web company in the northeast of Italy. And by the way, if you're interested, we are hiring. And there, in my daily life, I'm a PHP developer. But since I grew up as a mathematician, and now I'm a computer scientist, I have a big weakness for functional programming. And this led me to try Elm and to come here and share it with you. So just a little disclaimer before getting into some more serious stuff. I am not the biggest expert of the subject. I just tried the language, loved it really much, and decided to come here and share what I learned in the process. And just because I'm curious, who are you? So how many of you are front-end developers? Okay. Good part. How many of you are functional programmers? Okay, good. So how many of you are both? I could compute this, but if you raise your hands, it's easier. And how many of you already tried Elm? Is there somebody? Okay, somebody. Okay. And are you running it in production or no way? Okay. So just come to the serious stuff. What is Elm? So it's kind of a mouthful. You can say it's a statically typed reactive functional programming language that runs in the browser. So it's kind of long definition. Let's try to see what does it mean piece by piece. Let's start from the last one. What does it mean that it runs in the browser? That's the easy one. It just means that it compiles to HTML, JavaScript, and CSS. So you just write one file, one Elm file, and you run one simple command in your command line, and you get your HTML file containing HTML, JavaScript, and CSS. Okay, so next selling point, static typing. What does this mean? Well, it's different from dynamic typing, we are maybe more used to, and it means that just the type of a variable is known at compile time. So when the program compiles, you know if a thing is a string, it's an integer, it's something else. And this is a pro, in my opinion, because it leads to easier refactoring of the language, because every time you have a variable, you know what it is. And also, it helps you with testing, because you don't need to test for trivial stuff. I mean, if it's a string, I do this. If it's an integer, okay, the test do that. If it's undefined, then I need to do this checking. And also, another nice stuff from static typing is that almost all errors are catched at compile time. And this leads having no runtime exception in your client code. And also, errors are really, really nice in Elm. They help you. They are written to help you. So when you make an error, the compiler will say, hey, you did this mistake. You probably need to solve it this way, there. And if you need to know more, look there. And moreover, static typing also enforces semantic versioning. So when you want to release a new version, if you just change the signature of one of your function, you must release a new version. So this helps when you use NPM and you get new version of things. You are assured that the signature of the function you're using didn't change. And also another thing is hot swapping. What does this mean? It does mean that you just run your program. At a certain point, you click pause. You modify your code, and you just click play again, and your program will rerun the entire history that thing you already did with a new code. You just can modify your code while you're running it. So really cool. Then, other selling point, functional programming. I don't know if it's a selling point or not, but for me it's a pro. And why it's a pro? Because Functional programming, in its more broad definition, means just making things explicit, making inputs and outputs of function very explicit. So if you just think you have a function, just this lambda, everything that this function needs is specified as an input, and everything that this function produces is specified as an output of the value. The function itself cannot interact in any way with the state of your application. So it cannot read from the state, it cannot modify the state of your application. And this also leads to some performance optimization, because every time you have an input, since you cannot interact with the state inside the function, the output will always be the same, so you can cache things. But with this approach, we usually have a little problem, is that if all functions are stateless, that means you cannot interact with your state, and all your variables are immutable, so once you assign them, you cannot change their value, how can you interact with the real world? So how can you effectively produce some change with your application? Well, there are some possible solutions. The first one, and probably mostly adopted one, is just relax your requirements. I say, okay, maybe not all functions need to be pure and stateless, or maybe not all variables need to be immutable. I can mutate some of them, and you just relax, and you're more relaxed. Other option, maybe a little more abstract one, you keep functions stateless, you keep variables immutable, and you just start to play with function composition. And this is the approach that you get in Haskell, where monads are used to put state in some function composition. Or there is another way. And the other way is, the other selling point is functional reactive programming. So this is maybe the less known one. What is it? It's just a programming paradigm oriented around data flows and the propagation of change. How do you get that? You just try to make time as a first-order citizen of your language. And you do this having inside your language dynamic evolving values. So you have values that are holding to, well, you have, let's say, variables that are holding to a value, and without you doing anything to those variables, their value changes. This is kind of strange at the beginning, but wait a second, I will show you some example, and I hope that will become clearer. So this helps you because you can specify the dynamic behavior of your application completely at the time of the declaration. So you don't need to say, okay, this change, okay, I need to propagate the change there, just set something that get and set something over there. Everything flows by itself. So what are these dynamic evolving values I'm talking about? They are usually called signals. Just if you are JavaScript developers, you can think something like event emitters and observables. So event emitters are just things that when they want, they emit a value, the application reads this value that is emitted, and they do something with the value. Observables, on the other hand, are just objects holding to a value. When that value changes, there are other things in the application that are observing that value, and when the value changes, they react to that change. And that gives rise to reactive. The main difference between these two concepts and signals is that signals, they exist for the entire lifetime of the application. And the main important thing is that they always need to have an initial value. Well, let me give you some examples to make this concept more clear. So maybe the easiest example is the mouse position. This is Elm code. So we just want to show the position of the mouse. If I just go with the mouse there, you see the program is with nothing else that's showing the position of the mouse. And as long as I move the mouse on the screen, the two coordinates of the mouse are updating by themselves. Or another example could be just the last keyboard pressed on the keyboard. So as far as I press some key on the keyboard, just the signal keyboard presses updates its value. Okay, in Elm, we can have any signal. Signals in Elm are only things that represent real concepts. So, for example, the position of the mouse or the last keyboard pressed on the keyboard, but you can have also the dimension of the screen, other things related to user interaction, but also some more complicated things, as for example, the result of an HTTP remote call or some data taken from a database. And what does it mean that we have only real signal? It means that it's not possible for the developer to create or destroy a signal. We have just some pre-configured one that we can use. And we can also not create signals of signals, so do things too much complicated. This was done to keep things simple. And simplicity, in this case, led to some really nice abstractions. And so to just, from the signal, build something, we just connect them, setting up a static processing network. So we just define the relations that need to exist between those signals. And we do this defining what the so-called signal graph that usually looks something like this. This is just a really simplified version that in your application will get more complicated. So you will usually have some inputs that you will receive from user interaction, HTTP, and storage, and whatever. You take those signals, you transform them in a format that you like more. You can just use them to store some state inside your application. And then whenever you have all the signal as you like them, you merge them. Then you filter them and return some outputs. So let's try to focus on each one of these, let's say, boxes to look more closely how they work. So input, as we said, inputs are just signals from the word. So mouse position, keyboard presses, things like that. And the important thing is that we are not in control of changing these values, but it's the value itself that it's changing by itself and it's propagating through the application. So what we can do is not take one thing and move it somewhere else. We just say, okay, there is this relation between these two things, and the value will flow through our application by itself. To make this flow happen, we usually need to define some transformation. So we need to transform a signal into another signal. And to do this, there is this not complicated thing. There is just a map function. So what does this do? This is a function with two arguments. The first is a function that takes something of type A and returns something of type B. The second argument is a signal of things of type A, and we return a signal of things of type B. So what happens? Whenever we receive the values of the signal of type A changes, we apply the function, and we update the signal of type B. So not so complicated. Let's see an example. So again, keyboard presses. Actually, when I press some keyboard on the screen, some key on the keyboard, I receive the code of the character I pressed, and then I need to use the function from code that will just convert from the number to the character. And I'm sorry, what words? Okay. Everything's fine. Okay. What now if we want to store some state? Just, for example, we want to count how many times I clicked on the mouse button. Just really simple stuff, but still we want to store some state of what we already did inside our application. So to do this, we have a slightly more complicated function, but if we go through it, it's not so complicated. So it's called fold-p, which stands for fold from the past. So it's a function that has 3 arguments, and it returns its value. The first argument, it's a function that takes an input, the current state, it returns the new version of the state. So it's just one step. Then we take the initial value of our state. We take a signal of inputs, so all the things that happens, and we just use our function for every value of the signal of A. We apply this function to the current state. We get a new state, and at the end, we will get a signal of the new state. The important thing is not understand deeply how this function works, but it's that in Elm, application state lives all in one big full P. This is really helpful because it ensures consistency inside of the application. It's actually the same idea that you have in Flux, for example, if I use to Flux and Redux. And because this gives you a single source of truth for your application, it just means you do not have the need to synchronize between your components. The state is there. You just read from there. And it also makes very easy to do save of your state and undoing of your state. So going, let's say, almost back in time. And this leads also to some nice tool components. In Elm, you have a time travel debugger. So it's something that you can do something with your application, then click pause. You have a slide bar, you go back in time. You maybe hot swap something, change something in your program, and then you just replay your time. So this is just almost mind-blowing when you do some debugging. And how this full P works. So just give an example. So we have this full P function, and it's just counting the mouse clicks, starting from 0. Every time I receive a click, I take n and increase it by 1. So nothing really special. When I click the mouse, I see that the counter down here is increasing. Whoa. Okay, and now I have multiple signals now inside my application, and I want to put them together to have just one signal. I just do this with the merge function that just takes two signals and produces one bigger signal. Just one example with the nice dots moving. So I have three signals. One is tracking the mouse click. One is tracking the keyboard presses. One is tracking time. And you can see in the blue signal down there, we are tracking all the three things at the same time. Okay, but signals could be nice, but they are not so easy to work with because it's kind of strange concept we are not used to have in our application. We want to have them because they are really helpful, but we do not work directly with them. So what we need to do is abstract. So we just take signal as building blocks and we try to build some nice architecture over them. So in Elm, there is this thing so-called Elm architecture that naturally emerged from the language, and it's just a simple pattern for creating infinitely nestable components. And it turns out to be great for modularity, code reuse, and testing. So all nice properties. Go check it out. So the two main selling points of the Elm architecture are, as I said, modularity and extensibility. When you talk about modularity, the main strategy to make things modular is just to create nice abstraction, hide implementation details. So you just expose what other components could need from that component. And Elm helps you doing that because it gives you some nice abstraction boundaries between things. And in fact, you cannot inspect the structure of arbitrary values as you can do maybe in other languages, but it gives you, okay, this component exposes just this is what you have, deal with it. And to extend and put together these components, you just compose them, and you do that by nesting them. So you have one bigger component that is holding some subcomponents, each subcomponents have some more subcomponents, and so on, so on. You build a big hierarchy of components. And this nesting actually means delegation. So everything passes through the main one, and then just it delegates to the subcomponents and sub-subcomponents, and so on. So let's look in more details at the ARM architecture. It is built on 3 pillars that are just model, you're used to it, view, and the third is, it's not controller, it's update. Okay, and I'm going to show you what these are using a small application I built, and it helped me learn Elm, actually. And is, well, let me explain you what this does. Do you know joined in? Well, if you don't, it's a website where conference organizer can put their conferences with the list of the talks, and then attendees of the conference can go and rate the actual talks. So I was interested in having a list of the talks with slides, because I like just to download and read slides of conference talks. And I just use the joined-in APIs to get this data and show them on a single page. So not a complicated application. But let's go back to Elm architecture. So regarding the model, well, it's nothing else than a data structure representing the state of our component. And it's nothing else than the single source of truth of the component. For example, we were talking about conference talks. If you want to model that, one easy thing, simplified things, could be just have 3 strings, one for the title of the talk, one for the description of the talk, and one for the name of the speaker. That could be a representation of the conference talk. And okay, now we want to represent this in the screen. We have a model, we want to represent it. We use the view pillar. And to do this, we have just one function. It's a stateless function, pure function, that just takes our model and returns some HTML. As this is a pure function, stateless, it cannot interact with the DOM, so there is no mutation of the DOM here. What happens? Elm uses the virtual DOM, that is also nice from performances. So whenever this function returns a new version of our HTML, a diff of the old HTML or the new HTML is computed, and just a minimal diff is computed, and that minimal diff is lazily applied to our HTML and rendered on the screen. So let's look if we want to render our talk on the screen. How can we do that? This is the actual simplified implementation. So it's a function, we have our model, and returning some HTML. And so we just declare what is the HTML that we want. It's just a div that has a class talk containing 2 divs. One div just has a text with the title of the talk and the name of the speaker, and the other div as just the description of the talk. And so if we want to render this on the screen, I'm not a CSS guy, as you can see from here. It just renders something like this. But at this point, we cannot interact with it. We have no dynamical things in our application. So to do this, we need to go to the update section. And so how does this work? So in our application, we just declare some action that could take place in our application. So for example, we have a list of actions, and we just have an update function that is just takes an action, one of those, takes the current state of the model, and returns the new state of the model. So it's really simple. We just say how we need to update the model whenever we received one of those actions. One action is just a step in our application life. And if you think of this, then your business logic, whatever happens in your application, just becomes a sequence of actions. And this is really similar to what you have in domain-driven design and maybe you know event sourcing, where the story of your entities, the state of your entities is just computed by looking at their history, looking at the events that happen to them. Okay, and this gives you a clear representation of how the model can be transformed, actually. And if you want to look at the actual implementation, for example, in my simple example, I have two actions, one for tracking the click on the title, one for tracking the click on the description of the talk. And whenever I receive an action, for example, of type click description, I just go and update the state, the model, the talk, telling it, okay, your new description is got to be, we got a new description. Mind it, this is not mutation, this is just returning a new signal. No, it's not a signal, but a new string, a new model that it's going to substitute the previous one. So let's see this in action. So I have the same thing as before, but now if I go with the mouse and click, voila, we got a new description. And putting these pieces all together, what we have in the middle, we have our model or single source of truth, and whenever we receive a new action, it just goes through the update function and updates the model, and then whenever the model changes, the view function will re-render it and we will get a new view. This is just one step. If we want to make it more continuous, we can just, well, let's use signals. We will not see them in our application, but this is just how the application works. So we have a signal model. You can think the model as a function of time, how it evolves in time. You give it to it some action, a signal of action, so action that will arrive through time, and through the view function, you will update how your view will look like. But we still have another problem, and we need to have another round. What is the thing we are missing now? It's always the same thing. How do we interact with the real world? How can we do an HTTP remote call? How can we read some data from some storage? Because even if in functional programming we want to deny it, side effects are present. And the solution is not to treat them as side effects, but to treat them as managed effects. And with this I mean they exist, so let's just represent them as data. They are nothing else than some other components in our application. And what we have in Elm to do this is just another thing. There are ports. So ports is nothing else than the mechanism for sending messages inside and outside Elm. So your application could have a really nice boundary. Your application is this hexagon, and you can have just some ports that allow messages to come from the outside to the inside, and from the inside go to the outside. So we have two kind of ports. There are incoming ports that allow you to pass messages from JavaScript to Elm. And how do they look like? You just declare them in Elm. For example, this is a signal. Well, it's a port at the talk that is made if we want to add a new talk from JavaScript, from outside our application. So we declare it as a signal of 3 strings, a title, a description, and an author. And from JavaScript, we just call on that port the send function with 3 strings. And now this will bring this new talk inside Elm, and then inside our application we can process it. If you want to do the reverse, so pass a message from Elm to JavaScript, we have outgoing ports. So still, we have a port, and this time it's a concrete signal in Elm. For example, this is considered as a signal of a string that is defined elsewhere in Elm, and it's used for requesting talks. So now we want to make a remote HTTP call to retrieve from some API a list of talks for a given conference. And to do this, we just, in JavaScript, we just subscribe to this signal, to this Elm signal. So whenever the Elm signal changes its value, so maybe with a new string that is the URI we want to call, in JavaScript we just register a callback that will be called whenever the value signal in Elm changes. So, but this is still a bit low level. We want to abstract some more, to have some structure nicer to work with. And, well, obviously in Elm you get them. And they are tasks. They are just an abstraction to model side effects handled by the runtime. So they are just a way to describe a synchronous operation that may fail, and you just may think to HTTP remote calls or storage interactions. And in Elm, this work as lightweight threads, so you can have multiple of them running at the same time, and the runtime will just hop between them, not slowing down your application. They're just a similar concept to what promises are in JavaScript, almost the same thing, just a maybe nicer API. And as promises, they can be changed, so after you finish a task, you can start another one. So to grasp the concept a little better, let's go through the life cycle of a task. So first, inside of our Elm application, we describe an operation that we would like to happen sometime in the future. So we created an Elm, but it's not executed. To actually execute it, we need to hand it to a port. The port will take this task and hand it to the runtime. Then the runtime will compute and do the actual work. So how could this look like in Elm? Well, we have the same function as before, retrieve talks. Now we're using task and not just directly a port. Well, it just takes a string that is the URI we want to invoke to retrieve the talks. And when we pass the URI, we just say, runtime, just do a get operation, HTTP get. And if you fail, just return me an HTTP error. If you succeed, return me an action, in this case, talks retrieved action. We're still missing one thing, I promise is the last one, and it's mailboxes, because what we need is something that is able to retrieve values from the runtime. So we have ports, but we want to abstract over them. Now when we do tasks tell the runtime, okay, do this operation, but at this point we have not a mechanism to retrieve the value computed by the runtime. So we need mailboxes. They are just really simple. They're just a signal with an attached address. So why are they designed this way? Well, you can think at the address as something where we can send messages to. It's just like a physical address, the one we have at our houses. We can send messages, letters to them. And whenever we receive a new message at that address, then the signal that is composed in this mailbox will update its value. So if we want to complete our life cycle we had before of tasks, we were handing the task to the runtime. Now we are adding a little mailbox down here at the boundary of our application. So whenever we compute, the task performs, it computes a value, and when we describe the task inside Elm, we could have said, okay, when you computed the value, just put it inside the mailbox. And that value will go back inside Elm, inside our application, so we can do something more with it. Inside the Elm architecture, you usually abstract once more over tasks, so you can forget about mailboxes. And you do this with another thing that are called effects, and you usually use effects of action. So what are this? It's just almost the same things of tasks, so a synchronous operation. And when you perform then what you receive back is just an action that you will route again through the update function. So to do this, you just almost replace your model with a pair of the model itself and the next asynchronous operation you would like to perform, so an effects of an action. And you just like this, when you receive an action, you apply it to the model, and what you get back is a new model and the next operation that maybe you want to perform. So in our practical application, let's see, we have now two actions. So the first says, okay, we retrieved a list of conferences. And whenever we retrieve that list of conferences, so the update function will retrieve the conferences retrieved action, we just add those conferences to our model that it's joined in this case, and we say, okay, the next thing that you need to do is just perform this other task. So we're just receiving one task, and we say, okay, next thing you need to do. And then, in practice, it looks like this. You have the thing, and, well, no network probably. No, it's loading. Okay, first you receive the list of the conferences, and then for each conference is retrieving the list of the talks. Okay, okay, I'm done with this. Just some credits for the nice bullets diagram that I showed you before. Some resources, really helpful one if you want to dig deeper into Elm. And with this I'm done. Thank you for the attention. And speaker loves feedback, so if you want to give me some, I'll be very glad to hear it. Okay, thank you. Okay, I think we have some time for some questions. Just if you have some, wait for the mic. Wait for the mic, please.
How Elm is integrated with the graphical component of a page?
So
Angular has dual binding and this kind of technology. In which way Elm do this?
Well, you can just do your view part all inside Elm. Well, let me just try to go back. And you can just have all of your representation of the HTML done in Elm. And this is, in some sense, this is a two-way data binding because you're exposing the description of the talk, but this is nothing else than the string that you have in your model. So Elm, if you want, is just a complete suite for front end. If you want to integrate it with other components, for example, you mentioned Angular, I guess, or if you want to use, I don't know, React or some other things where you already have some code, some things done, well, at the moment you need to go through ports, and that could be a little rough, but it's really nice for keeping your things modular. So if you want, in Elm, you can do a lot of stuff. If you want to integrate with other external components, you could do that, but maybe it's not the nicest developer experience. Okay.
What about the performances of ELM programs?
The performances, okay, so I don't have a slide on performances, but the performances are really good actually. Well, if you look it up online in the Elm website, there is a blog post about performances of Elm rendering, and they are really good. They, at least when that profiling was done, it was like 1/5 or 1/3 of React, and much better than Angular. There still are some other JavaScript frameworks that performs better than Elm. For example, you have some Om or Mercury or Mithril. They are really, really, really fast compared to Elm. But yeah, Elm is still very fast, and I think that's not the main selling point of Elm. performance. I think the main selling point of Elm is just you can write your business logic in a very clear and expressive way. So you still get nice performance, maybe not the best one that you can have in the JavaScript world, but it's completely another world from other points of view compared to JavaScript. Wait for the mic, please, just for the camera.
Yes, a question about the community. As you know, obviously, the main author of Elm is, I can't remember the name, this guy which has been employed by Prezi now, right? So are there
Actually, it was. It's no more a Prezi right now.
Really?
You're referring to Evan Saplicki?
Yeah, exactly.
That's the creator of Elm.
Yeah.
And you were, well, finish the question so I can...
Yeah, one question basically was, is there all, is there other committers? Is the community larger by now or something?
Okay,
thanks.
I don't know if he's the only one working at the core of Elm right now, but the community is really expanding. Right now, I don't know the exact numbers, but I think there are something like 35 meetups all around the world, Elm meetups, specific Elm meetups. I know that in San Francisco, usually at the meetup are around 100, 150 people meeting there. As far as I know, there's nothing in Italy, but there is something in Berlin. There is something else in Finland. Well, maybe not so easy to reach them. But anyway, the community is expanding. There's many people working on the language, creating tools. I think that Evan Saplicki, this is the creator, is maybe the only one working on the core of the language. And yeah, the development of the language is not so fast. So probably the last release was November 0.16. 0.17 will probably come out next month. So you have almost like 6 months between one release and the other. But this is also a choice by the authors because they do not want to give a lot of functionalities that people could use, a lot of freedom. They will just, okay, we will give you what you need. Right now you learn to use those tools. You learn to do things well. And then when you learn to do things well, we will give you whatever you want so you can do things. So you already learned how to use the language, you know how to do things well. And also if you have tools that allow you to do things less well, you will not do it because you're already accustomed to do things well. Okay.
Can you show us?
Yeah, Mike, please.
You mentioned the nice compiler errors. Can you show us one real quick? You have the possibility.
Oh, let me check. Yeah, I can. Give me a minute. Just need to open my project. Okay. So, okay, let's put the console right there. No. Okay. So, C project. My stuff first. Okay. So reactor. So this is part of the tooling you have in Elm. So you have a reactor. It's just something that will make things run in the browser. And now. This is this is the code of my application. And so, yeah. So let me just make a typo somewhere. So I say that, well, this init is not a string, but it's an int. I decided that this is an int, but somewhere else in the application I'm passing it a string. So now we need to actually go in the browser. I can go to the nice place, localhost, go to joined in Elm main. Okay, let's enlarge this. Okay, so it says the type annotation for init does not match its definition. So the type annotation is saying that we need an int, but from the code, I'm inferring that it needs to be a string. So that's one example. You can find several also online. But there's also a nice thing in Elm. They have a repository for errors. So if you use Elm and get an error that it's not an error message that does not satisfy you, you can just go to this repository, open an issue, telling I would like to know more when this error happens. And then the Elm community will just work on it, work on the compiler to make that error more expressive. So you can also improve on error messages. That really, the main idea is that the compiler is your friend, because it's functional programming, so usually when things compiles, they work. But getting them to compile is the hard stuff. So if the compiler really helps you doing things, finding errors, it tells you, okay, go there, change that thing, the process is really easier. Okay? Okay, thank you again.